Hi, everyone. Welcome back to Psych 3510. In this lecture, we're going to discuss variability. So, the last time we left off, we were discussing measures of central tendency, which is the things like mean, median, and mode, sort of the middle ground of data. And in this topic, we're going to discuss the spread of data, or how data can vary, i.e., variability, around that mean or that measure of central tendency. So, as a start, we have multiple measures of variability. So, for example, we have the range, the interquartile range, variance, and standard deviation. So, my guess is that you are very familiar with number one, perhaps number two, but you are not very familiar with numbers 3 or 4. So, moving forward in this lecture and moving forward in this class, we're going to briefly sort of move over numbers 1 and 2, the range and the interquartile range. However, variance and standard deviation are going to be most important to us in this class, because these measures of variability, again, how scores can move around the mean, are going to be most important to us. So just know that these are the four major measures of variability, but we're going to focus on numbers 3 and 4. So I do want to take a moment, in case you haven't sort of understood the concept of variability, to maybe explain the base concept a little more. So if we take any measured variable, let's say height, right? So the average height of a human might be 5'8", 5'9", right? If we combine men and women. And so if the average height is, let's say, 5'9", some people are 6 feet tall, some people are 5'5", some people are 6'6", 6'10", some people are 5'1", right? Like, so the average is 5'9", but people vary around that mean. And that's the idea of variability, is that there is a score, the mean, that describes the most likely or the best score from that data set. But we have to understand that people do not adhere to that mean exclusively, right? People vary around the mean. And this idea of variability is really important in statistics, because it tells us how, for example, effective a manipulation is, right? So in general, we want less variability. If I give you a medicine and there's lots of variability in the impact of that medicine, then it means the medicine has differential effects. It's not a good medicine. Versus if I give you a medicine and it has low variability, meaning everyone is like really close to each other, the effect of the medicine is very similar to one person to the next in that group. If the variability is less, it means the medicine is more consistent, it's more effective. We can rely on that medicine more. So variability is really important in the context of an experiment where we're doing like different things to different groups of people, because the idea is that we want the effect of one treatment to be consistent within that group, and we want the effect of the next treatment to be consistent within that group, because that means that the treatment means something, it's doing something. Okay, so I just talked a whole lot about variability. If you have any questions about that, please email me. It's a weird concept, but if you can understand it, it's really important for sort of moving through the rest of the class. So we're going to tackle each of these four measures of variability, each in turn. We're going to spend a little bit of time on the first two and most of our time on numbers 3 and 4. Okay, so like I just said, central tendency is not enough information if we want to describe a set of data. So here we see a graphical representation of two distributions that have the same mean, right? So this vertical line is our mean, and we have distribution one, which is this tall distribution, and then we have distribution two, which is this more flat but wide distribution. So the idea here is that even with the same mean, groups of data can differ in the amount that individuals differ around the mean. So, for example, let's stick with height. Let's say that this vertical line is 5'9", right? That's our average. And so, in this first distribution, this really tall distribution, most people are around the mean, right? We're packed into the mean. The height of this distribution means the frequency of occurrence of that data point, such that people cluster around the mean in this distribution. However, in distribution two, people vary much more. So if this is 5'9", then we have a lot of people over here at 6'6", 6'9", 6'10". We have a lot of people over here at 5'2", 5 foot, 4'10", right? There's more breadth in the distribution. So distribution number one is tight. It has less variability around the mean. Distribution two is wide. It has more variability around the mean. And so this is important because we would not want to treat these two groups of people as being the same just because they have the same average or the same mean, right? So these two groups of people might both average 5'9" for their height, but they are very different groups of people because group number one, everyone is tight around 5'9", and group number two, everyone is like very spread out. There's lots of tall people, there's lots of short people. So the groups are very different. And in the case of experimentation, where the goal is essentially to put people into groups and then compare them, what that means is that variability, the amount which a group of people spreads or varies around their mean, matters when we evaluate the effectiveness of an experiment. Here's another example. So let's put this in terms of exam scores. So let's say this black vertical line is a C, right, like a 75, like a perfect average score. The gold class, right, lots of people get C's, but very few people get A's and very few people get F's, right? We're condensed around the average. The green distribution, as we sort of flatten it down, we have fewer people getting C's, but we have more people getting A's and B's, but also more people getting D's and F's, right? We are more variable in the distribution of our scores. And of course, the blue group is even more variable, right? Fewer C's, and we're spread out along the continuum of the grades. Okay, so that's like conceptually what variability is. I would suggest stopping and replaying this if you're not quite understanding the idea of variability, because when we're going to move forward from here on out, we're going to be discussing like the content of variability, the calculations, the specifics. So if you're confused about what variability is in general, please go back and rewatch like the first, I don't know, whatever, 10 minutes of this lecture. Okay. So our first most simple measurement of dispersion or variability is the range. You order all your values from low to highest, and you subtract the highest from the lowest. Easy peasy, right? It gives you the idea of like how far apart your highest and your lowest values are. The interquartile range requires us to do essentially like median splits. That's the best way to describe it. So if we have these data, right, these are our number of Facebook friends, I believe is the example. So we have the individual number of Facebook friends that people have. We order them from lowest to highest. We find the median, and the median splits us in half, right? And so if we want quartiles, right, what does a quartile mean? A quartile means fourths, right, quarters. So if we have the upper half of our data, we find the median of the upper half, right? So we have 1, 2, 3, 4, 5 data points above our median. We find the median of the upper half of our median, and it gives us the upper quartile. We do the same thing for the lower quartile, right? We have 1, 2, 3, 4, 5 data points below our median. So we find the median of the data below the median. And these 3 data points, right, the lower quartile, the median, and the upper quartile, will split our data set into even quarters. So we have the lowest quarter, the second lowest quarter, the third quarter, and the fourth quarter. So again, for interquartile range, all you're really doing is a bunch of medians. So we find the median of the data, then we find the median of the upper half, then we find the median of the lower half, and that gives us this quartered range of data where we can say this is the upper quartile, the second quartile, the third quartile, the fourth quartile, so on and so forth. Okay, so all of that is nice, all of that is good, but those things are not the most important measurements of variability for science. The most important measure of variability for science is something called a standard deviation. And so what we're going to do for the rest of the lecture is explain how we calculate a standard deviation, what it means, and then you're going to have, I think, 3, forgive me if I'm wrong, I believe 3 practice problems at the end for you to work through at the end of this lecture. So to calculate a standard deviation, which again is our best, our most valuable measurement of variability, we have to start with something called deviance. Deviance is basically the amount that a particular score deviates from the average of that group. So, for example, if I have a group of people who average 5'9", and some individual person is 5'11", it means they deviate by 2 inches from the average, right? It's their individual deviation from the mean of the group. So the first thing we want to do, if we want to assess how much people vary in a group, we want to assess how much each individual deviates from the mean of that group. So this is the formula for deviance. Each xi, so each individual, and its distance from, right, minus the mean. And then we're going to see that later in a few steps, we want to total that deviance. We essentially want to add it up because it's going to tell us something interesting about variability. So let's take this example. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 individuals. We have calculated or recorded the number of Facebook friends that each of those 11 individuals has. And we have the data here to our left on the left side of the screen. So the first thing we want to do is find the average or the mean of that data, right? And it happens to be 95. So the first step to calculating deviance is you have to know the mean. So you take your data and you add it all up, you divide by how many there are, and it gives you the mean. The mean in this case is 95. And now we want to know how much does each individual deviate from the mean. So up here on the top right, we take our formula, each individual score minus the mean gives us deviance. So 22 minus 95 is a negative 73 deviance because this individual is 73 friends below the mean. 40 minus 95 is 55 friends below the mean, so on and so forth. We can see that people who are above the mean have positive deviance values. So we take each individual, we subtract their score from the mean, and we get a deviance. One thing to note about deviance is that when we add it up, when we get a total deviance, it will always be zero. Always. In fact, I mean, that's like the definition of what it means to be a mean, right? The average. The definition of the average is the place in the data in which the deviance evens out, right? Is zero. That's what it means for something to be an average. So if we calculate these deviances, they will always add up. They will always sum to zero. So this is good. It tells us something about the manner in which individual scores vary from the mean. But in general, mathematically, like numerically, we don't like things that add up to zero. They don't do as much good in terms of like understanding things about the data. We don't like zero. Zero gives us no information, right? The total deviance gives us zero information. This is information, right? These values of minus 73, minus 55, minus 42, so on and so forth, up to 21, 26, 139. That's information. Zero is nothing, right? It's zero information. So we don't really like total deviance. What we want to do is we need some calculation that will take the distance of each score from the mean, the deviance, and turn it into something valuable arithmetically for us. What we call that, and I know this looks really scary, is the sum of squares, SS. So let's break this down. We have 11 individual scores. We found their mean, right? We added them all up. We divided by 11. That equaled 95. We took each score and we found its distance or its deviance from the mean. Some are negative, some are positive, right? Based on whether they're below or above the mean. But if we add all these up, they equal zero, and zero doesn't help us. Zero is zero information. So we need something that we can do to these values that retains their relationship to the mean, but allows them to not add up to zero, to not sum to zero. So the best, most efficient arithmetic way to do that is to square our deviances, right? If I square all of these values, they retain their arithmetic relationship to each other because I'm doing the same arithmetic to all of them. But if I square these negative values, they become positive. And if I square these positive values, they stay positive, which means I can now quantify them. I can add them up. I can sum the squares, right? That's why this is called the SS, the sum of squares. I can sum the squared deviations of my deviances and have some kind of idea about how much my individuals vary around the mean. So we take our deviances, we square them, and we get this, right? Negative 73 times negative 73 equals this, right? Square each of these values, and you get these values on the right. So I'll take a minute, look at this, make sure you understand what's happening. We took our scores, we found the mean, we subtracted from the mean, and then we squared the deviance from the mean. This formula up here on the right is the sum of all individuals minus the mean squared. Right? That's essentially what we've done here. We've taken each individual minus the mean squared, and then we add them all up down the column to get a sum of squares of 32,246. So this number actually represents like a quantification of the deviance of the individuals from the mean, such that the larger this value, the more that people vary from the mean. The smaller this value, the less people vary from the mean. So this is like super valuable. Like this is exactly what we wanted in terms of a measure of variability. It's a single number that tells us how much or how little a group of people vary around their mean. But there is still a problem with this number. So notice that the values that vary the most from the mean contribute the most to sum of squares, and the values that vary the least from the mean contribute the least to sum of squares, right? So if you are close to the mean, then you don't deviate very much. As such, you do not contribute a large value to the sum of squares. If you deviate a lot from the mean, you contribute a large value to the sum of squares. So the problem with sum of squares, and I know this is a lot, I know it's like step by step by step of like the theory behind the math, but it matters, trust me. The problem with sum of squares is that it's dependent upon things like the number of items or the number of scores in your data set. So the more data you collect, the larger your sum of squares will be because you have more data points. And so we don't want a measure of variability that's dependent upon the number of scores or the number of data points. So a more useful alternative is the average dispersion. So essentially what we call the variance, which is the mean of every individual minus, the sum of every individual minus the mean squared divided by n, how many individuals there are. So we take sum of squares, we take this formula up here, right? Nothing has changed. We take this formula, that's our numerator for variance, and we just average it. We average the dispersion from the mean. So the sum of squares divided by how many individual scores we have assessed. So what we call the variance is essentially the average of dispersion around the mean. So we would simply take this sum of squares, right? We have our values, we found our mean, we found the deviance from the means, we squared the deviance from the means, we added them up, and then we take SS, sum of squares, we divide by n, which is our number of individuals, and it gives us variance, 2,931.45. It is essentially the average amount of variability per person around the mean. So this is nice. It's good as well. We like variance, but it's still not quite the arithmetic that we need because it is still dependent upon the essentially form of the measurement. So in this example, variance gives us a measure in units squared, right? So if we're talking about Facebook friends, right? This person has 22 Facebook friends. We subtract from the mean, they have 73 Facebook friends less than the average. That gives us a squared deviance of 5329. We average that, and we're still left with essentially a squared friends unit, right? So we squared the number of friends when we did sum of squares. And so even though variance tells us, excuse me, the average deviance of each individual, what it's telling me is the average squared deviance. And that's not good because if we think about the unit here, right, the measurement value is Facebook friends, right? How many Facebook friends do I have? So I want my eventual measurement of variability to be in the units of Facebook friends. What I currently have is a measurement of variability in the units of Facebook friends squared, right? Because I squared these values and I haven't done anything to unsquare them. So the variance of 2,931.45 is informative and valuable, but it's not quite what we want. What we want is what's known as a standard deviation, which is simply the variance, right? The sum of every x minus the mean squared divided by n. And then we take the square root of the variance. So again, I'll say that one more time. We have all of our values, right? All the individuals that gave us scores on Facebook friends. We found their mean. We found the deviance. How much does each individual vary from the mean? We squared those deviances so that they sum to something other than zero. We summed them. We found their average, right? We took the sum of squares, we divided by n in order to get a variance. That variance is good, but it still exists within the arithmetic of a squared friend, right? And a squared friend doesn't mean anything. So we want to unsquare the friends. So we take the square root of the variance, and that gives us the standard deviation. So the square root of 2,931.45 equals 54.14. And finally, we have a standardized measure, a single value that tells us the essentially average spread or dispersion of a data set. Standard deviation. That's why we call it that. How much do the individuals within this data set standardly deviate from the mean? 54.14 deviation points, right? And so we can take this standard deviation, and even though this group is talking about Facebook friends, we could compare it to height. We could compare it to weight. We could compare it to depression, because we have taken away the units of the measurement, and what we're left with is a pure numeric evaluation of how much do individuals in a group vary around the mean of that group. And that's what we want, because variation matters, right? If I told you that I have a medication that will make you happier, right? It'll increase your happiness points by 5. That's great, right? I would like 5 more happiness points. Thank you very much. But if that's the average of an increase in happiness points, something you also want to know is, well, how much does that vary around the average? Because if some people decrease by 10 happiness points, if some people decrease by 20 happiness points, some people increase by 10, 5, 15, 25, like the variability there matters when I make a decision about this medication. Because if this medication is going to make me happier, if it's going to reduce my depression, I would like for it to have a lower standard deviation, meaning the effect is homogeneous. The group of people who took the medication have less variability around the mean. That's what I want, because I want the effect of the medication to be consistent across people. Whereas if I have a medication that's very inconsistent across people, it has a high standard deviation, it has lots of variability. It means the medication like works for some people and it doesn't work for other people. And frankly, that's not what I want in a medication, right? I want consistency with a medication. So standard deviation is the arithmetic way we calculate how much around a mean a group of people vary, so that we can make assessments of essentially the consistency of the effect that we have put on those people in an experiment. That's a lot. I know it's confusing. I know it's a way of thinking about numbers conceptually. Like I said, nothing about this is arithmetically difficult. The calculations are very simple. The theory, the idea behind the numbers is what's potentially problematic. So, stop here if you don't quite understand what standard deviation is. Go back, rewatch, reread everything, because moving forward, we are going to be calculating like examples essentially. So go back, rewatch, and then come back to here for some examples. Okay, so if we're talking about distributions, right? So groups of people with data, then they can have the same mean. So the blue group has the same mean as the red group, right? They're both on the average is 50. However, the red group has a larger standard deviation, meaning people are more likely to be variable around the mean, right? They're more likely to score 20, 25, 30, 70, 75, 80, whereas the blue group is very tight around the mean. The vast majority of the people are right around the mean, so we have this high distribution. They're right here around 50. So visually, this is kind of what a small standard deviation, the blue group, versus a large standard deviation, the red group, looks like. Okay, so this brings us to the idea of what's known as the normal curve. The normal curve is a symmetrical, approximate distribution of scores around a mean. The idea being that with enough data, with enough people, data points, then the mean will be the most likely score, right, in the middle. And most people are around the mean. As we move away from the mean, then the likelihood of that score gets less and lower. So if the mean height is 5'9", it means there are very few people who are 4'10", just like there are very few people who are 6'10". The more extreme we get from the mean, the less likely the occurrence. And so the idea here is that we can sort of fit our standard deviation calculation to this curve for any given variable, such that we can assess the likelihood that someone is around the mean versus the likelihood or the score that would be required to be away from the mean. So the closer you are to the mean, so the sort of large portion of this curve, it means that there's a greater percentage of people there versus if this is our like benchmark, if we say, okay, how many people are 6'5" or above? Well, it's very few people, right? Because 6'5" we can judge and we can calculate as being above the mean of 5'9". So if this is 6'5", there are very few people above that value because that is a high standard deviation versus most people who are below that value. So what the mean plus the standard deviation allows us to do is assess essentially the likelihood of any given value. So if I said your IQ is 115, I could fit you to this curve if I knew the mean and the standard deviation of IQ, and I could tell you how likely or how unlikely your score of 115 on an IQ test is. So it allows us to make assessments of whether the amount of variability in a score is an extreme amount of variability or whether it is a common or expected amount of variability. So this is going to become more important in this section as we move into things like z-tests, z-scores, and we add hypothesis testing to the idea that I could take an individual and I could say, okay, you are this tall, and if I know your height, if I know the average height, if I know the standard deviation of height, I can assess how tall or short you are in comparison to the rest of the population. So that's when this becomes really valuable for decision making. Okay. So the rest of this lecture is just practice with data and getting you all the way to a standard deviation. So I'm not going to go through all of this talking. It's just obvious from the numbers and the data, but I want you to practice. I think there's 3 of these. I want you to practice each of these calculations. Take these data on the left, find their mean, find the deviance from the mean, right? The x, the value minus the mean, square that deviance, sum those square deviances, divide by n to find the average amount of deviance, then take the square root of that value to give you a standard deviation. So walk through these. If you need to use the first one sort of step by step like this, please do. There are multiple examples. As you can see, I'm just sort of breezing through them really quickly. Do those practice problems. One of them is your workshop for this section, so make sure you do it by hand, and then upload your workshop credit. And let me know if you have any questions about variability. So, thank you very much. I hope you enjoyed this theoretical lecture about variability as much as possible, and I will talk to you later. Thanks.